Good morning, welcome back to 5 Minute of Code. This is day 21 Dirac dice. And my plan for today is to concentrate really hard and not make blunders. There's not much to do as you slowly descend to the bottom of the ocean. The submarine computer challenges you to a nice game of Dirac dice. This game consists of a single die, 2 pawns, and a game board with a circular track containing 10 spaces marked 1 through 10 clockwise. Each player's starting space is chosen randomly, your puzzle input. Player 1 goes first. Players take turns moving. On each player's turn, the player rolls the die 3 times and adds up the results. Then the player moves their pawn that many times forward around the track, that is, moving clockwise on spaces in order of increasing value, wrapping back around to 1 after 10. So if a player is on space 7 and they roll 2, 2 and 1, they would move forward 5 times to spaces 8, 9, 10, 1, finally stopping on 2. After each player moves, they increase their score by the value of the space their pawn stopped on. Players' scores start at 0. So if the first player starts on space 7 and rolls a total of 5, they would stop on space 2 and add 2 to their score, for a total score of 2. The game immediately ends as a win for any, so I'm actually going to write down. The circular track is 1 to 10. The players are 1 and 2, but the score starts at 0. So if the first player starts on space 7, the game immediately ends as a win for any player whose score reaches at least 1000. Since the first game is a practice game, the submarine opens a compartment labelled deterministic dice, and a 100-sided die falls out. This die always rolls 1 first, then 2, then 3, and so on up to 100. 1, 2, 3, ... 100, back to 1. After which it starts over at 1 again. Play using this die. For example, given these starting positions, 4 and 8, this is how the game would go. Okay. Since player 1 has at least 1,000 points, player 1 wins and the game ends. And it looks like in that example, the wrapping back to 1 after 100 thing isn't even necessary. At this point, the losing player had 745. The die had been rolled a total of 993 points. So it's losing multiplied by number of rolls. Play a practice game using the 100-sided die. The moment either player wins, what do you get if you multiply the score of the losing player by the number of times the die was rolled? And actually, I might take the input on the command line rather than from the file, because it seems easier. So, we start out at 0, which means the first roll is going to get us 1. And then, once we've rolled 100, the next time round, this gets to 101, which is greater than 100, so we get 1. I think that's going to do the job. And they both start out on 0 points, don't they? What I might actually do is pos equals so to play, you roll the dice. Your score gains then. Oh no. What does your position on the circular track mean then? Increase their score by the value of the space the pawn stopped on. So, position of P, if it's greater than 10. So it's 1 plus this minus 1 mod 9. Let's see if that is actually correct. So if pos p, forget n, or forget pos p. If n is 1, then we get 0 mod 9 plus 1, so we get 1 out. If n is 10, then we get 9 mod 9. This wants to be mod 10 still, I think. Because we want 0 to 9 to come out. So if n is 10, then we get 9 mod 10, which is 9, so we still get 10 out after we've added 1. Yeah, good. That sounds correct. And now our score increases by whatever position we landed on. And if it's greater than 1,000, is it greater than or equal? And does player 2 get to have a turn after player 1's won? So that they've each had an equal number of turns? No, he doesn't. The losing player multiplied by the number of rolls. So we could calculate die in terms of n rolls as well, but this will be fine. I think it was greater than or equal, wasn't it? At least 1,000, so that's greater than or equal. So then we've won, so what number of rolls multiplied by the losing player's score, so that's score of not P. And then we're done. Pos is defined in the standard library for stupid reasons. Oh yeah, so is die. There's a different kind of die. What was that really for? Okay. What was the example? 4 followed by 8. And there's a, I think there's a delivery here. Right, let's see what that says then. 4 and 8. So the die roll did wrap on the sample input. Oh, you do 3 rolls, don't you? That's the problem. I think you do 3 rolls per turn. Rolls the die 3 times and adds up the results. So we'll just go roll plus roll plus roll. I don't think we need this anymore. So maybe the die didn't wrap on the sample input. It makes sense that our number is about a third of what it should be, if we should have done 3 times as many rolls. I think that was correct. Yes. Great success. Okay, now that you're warmed up, it's time to play the real game. A second compartment opens, this time labelled Dirac dice. Out of it falls a single 3-sided die. As you experiment with the die, you feel a little strange. An informational brochure in the compartment explains that this is a quantum die. When you roll it, the universe splits into multiple copies, 1 copy for each possible outcome of the die. In this case, rolling the die always splits the universe into 3 copies, one where the outcome was 1, one where it was 2, and one where it was 3. The game is played the same as before, although to prevent things from getting too far out of hand, the game now ends when either player's score reaches at least 21. Using the same starting positions as in the example above, player 1 wins in 4,443. Oh, okay. Yeah, player 1, okay. Determine every possible outcome. Find the player that wins in more universes. In how many universes does that player win? Well, we know that if you're on a given position with a given score, then it doesn't matter how you got there. So how many positions are there and how many scores are there? There are 10 positions and there are 21 possible scores. So we can definitely just count how many ways there are to reach. So to reach a given score at a given position, you can either roll a 1 from the position before and the score before, or you can roll a 2 from the position 2 before and the score 2 before, or you can roll a 3 from the position 3 before and the score 3 before. So this sounds like dynamic programming. So let's try and do that. Being careful to concentrate and make no blunders. Actually, well, do we want to use part 1? I don't think so. Sorry, we'll use part 1. So, we don't want this deterministic die. We do want the win function, we do want to read the command lines. I don't think we want this. Oops. What we want instead is a table that will tell us the number of ways that each player has reached each position with each score. So, for the table, we've got 2 players, 10 positions, 21 scores, and they'll all be initialized to 0. But what we want is a table of player 0 at position they start at score 0 is 1, and the same for player 1, because there's one way for them to reach that position. Sorry, that's score 0. And then let's make that go a bit more than 21. I don't think we're tight on memory, are we? That's going to be 600 elements. 2 times 10 times 30. So while s is less than or equal to 21, we know that well, actually, we'll do a function call there, I think. So we'll calculate for player 0 score s, we'll calculate for player 1 as score s, and then at the end, these need to be big ints. I really need a multi-dimensional array function that also takes a constructor, so I could do something like that. Just going to loop over them, I think. Table 0 ij. Big new 0, and table 1 ij, big new 0, and oops, that doesn't, ZB doesn't work in my editor. So ZZ puts the current liner on at the middle of the screen, ZT puts it at the top of the screen, but ZB puts it 7 down. What if I put yeah, it works there. but it doesn't work if the file is shorter than the screen. Okay, fine. We need to set table 0 of player 0's starting position with score 0. Oops. We need to 1. The same for player 1. They need to be big ints because the numbers get so big. So what will count do? This takes a player and a score, and we know that, well, score is going to start as 1, so table of player for each position. So, okay. Call the player I. Call the player P, we'll call the position I. And the positions are called 0 to 9. So this wants to be, or should we just call the positions 1 to 10? I think calling them 0 to 9 is fine, as long as we remember we get one more point than the position. Oh, hang on. I think we might call the positions 1 to 10. So, let's write down an example. How many ways are there to reach position 5 with score 10? Well, we know that we either rolled a 1, or we rolled a 2, or we rolled a 3. But we could have been in any of the 10 previous positions. So let's say if we were in position I with score J and we rolled a 1, 2 or 3, would rolling a 1, 2 or 3 land us on score S? So, we're in position I with score J. In position I with score J of 1 equals S. Then we know that we need to add to table of P as player. Okay, so table of player, the position that we land at. So actually let's just go maybe roll from position player So if player is in position I, score J, roll a 1, does that get us new score? And we'll do the same for 2 and 3. So what maybe roll has to do is work out if we were in position with old score and we roll, where would we be? So new pos equals 1 plus pos plus roll minus 1 mod 10. Is that what I wrote in part 1? So let's just check it and not make blunders. You roll 3 dice. Position plus n minus 1 mod 10. But you roll 3 dice. So the way we'll do that is 3 times 3 times 3 is that 27. So how many calls to maybe roll are we going to have? For one call to calc, we're going to have 10 times score times 27 is 270. We've got 2 players, so it's 540. Multiplied by the score, which is 21 squared over 2 times 540. We're going to have 120,000 calls to maybe roll. Maybe that's okay. The thing is, a lot of these will actually add up to the same score. So instead of calling maybe roll, how many possible scores are there? Well, the minimum is 3 and the maximum is 9. So there's only 7 possible scores. So instead of, that would be a factor of 3 better if we just calculated how many possibilities there are for each one. Which maybe, what we'll do is we'll put a note. If too slow, work out the number of ways to roll each of 3 to 9, and to give maybe roll a factor of factor to add. So then maybe roll. Right, okay. Maybe roll then knows that we can add to table of player of new pos. Oh, okay. If old score plus new pos equals new score. Maybe we don't even need to do that. Maybe we just... No, we'll do it this way first. But maybe we don't need to take in a new score argument. But it's harder to convince me that the dynamic program is correct without that. So if we've landed on the score we're looking for, is it still a track of 1 to 10? That seems like the game might end quite quickly. I've realised another problem. We need to know how many turns it took to reach the score. Yeah, that's what we need to do. Okay, so instead of player position score, we need player position number of turns score. Since the minimum roll is 3, the minimum position is 1, then the maximum number of turns is 21 divided by 4, which is 6. And their initial score is after 0 turns. So we don't want to take a new score here. What we want to take is number of turns. and it's no longer a maybe, it's a definitely. So we don't take score, we take number of turns. This feels like I'm confusing myself. So what did we say that I was? I is 10 possible positions. J is not less than S. We don't want a J. On each turn, we can be in 10 possible positions. So this comment is now wrong. What we want to know is, for the 10 possible positions, we want to go over each possible old score in here. You can actually roll up to 10 points, can't you? So maybe we want more than 30 possibilities here. Probably 31 would be enough. So, the table tells us the number of ways we can reach a given state. So we don't take an old score argument either. Yeah, this is looking better actually. So, table player, new position, then its number of turns, and then its score. After n turns, I think this can be 21, because if we reach 21 in the last turn, then we don't need to be able to win this turn, we've already won. Maybe we just, well, let's say that for now. So the new score is S plus new position. And we want to add to that what the old score was, which was table player pos turns minus 1 S. So that says the number of ways we can reach this point in the universe graph gains however many ways we had to reach the point that we came from. And then at the end, how do we calculate how many ways can a player win? They have to reach a given score in fewer turns. They have to reach at least 21 in fewer turns. Right, we call him player 0, don't we? Do we think this looks right? So what we're saying is, after 5 turns, so we go 1, 2, 3, 4, 5. Starting on 0 points, what's the minimum number of points you can have? It's going to be 5 times 4 is 20. So we want to do an extra turn. So now we want to go how many ways did each player, in how many universes did each player win after T turns? So that is simply, for player 1 wins if he reached 21, if he had at least 21 points on this turn. Player 2 wins if he had at least 21 points on this turn, but only if player 1 did not also win. Well, let's see if we can work out how many. We'll forget the tiebreaker for the time being. We'll just say, we'll just count it for both, and then we'll check if player 1's score is correct, and then we'll look at the tiebreaker. So, the table is player, position, turns, score. So, oh, but we only won on this turn if we didn't win on the previous turn. So I want to add to win P, table of player, position, turns, score. So we're counting how many different ways each player can reach 21 or more. So calc says on turn T, where can we possibly end up? Well, let's just see what it says. Oh, we don't use this anymore, do we? So how long do we think this will take? While it was compiling, I worked out the number of ways to roll each number. However, it may be that doing a bunch of additions is... Oh no! Doing a bunch of additions might actually be quicker than doing the multiplication. How did we run out of memory then? Well, we're not allocating anything in here. 11 times 40 times 7 times 2 is 6k big ints. If they're 4 words each, then that's 25k of memory. And how large were the numbers in the sample? 48 bits. A bit more than 48 bits. So we do need 64-bit ints. Well, let's see what that says then. We actually know that we don't need 40 possible scores because we only go up to 21 here and the maximum new pos is 10. So this only needs to write to index 31. So 2 times 11 times 7 times 32. That's going to be about 20k of big ints. 20k words usage of big ints. Ah. So it didn't run out of memory that time. Good. How long is it going to take? It's 11:02 now. I should have made it print the number of turns it had got to. I might stop it and make it print the number of turns. Oh. Well, I think the numbers are wrong. 27029 for player 0. Yeah, the numbers are wrong. Let's see, what could the problem be there then? I'm going to do the multiplication thing. So we'll make a temporary number here. So I'll take an argument saying the number of ways, and then what we're going to do is just roll PI1, no, sorry. Three, there's one way to get it. PI4 has 3 ways. Hang on. 136. 5 has 6 ways. 6 has 8 ways. Don't need to bother doing the multiplication if it's not 1. And if it's 3, I wonder if just adding it on 2 more times would be faster than doing the multiplication. Don't know, we'll leave it at that for now. And then not always turn 1, is it? So the number of ways that we could win in, but we haven't won in any universe where the other player has won in 1 fewer turn. So we'll make win actually take the number of turns. 2 players, and how many turns did we say there were? 7. Okay, and then having done that, the number of players player 0 can win after t turns is equal to wins 0t minus w1, and then w1 is equal to wins 1t minus w0, I think. But obviously in terms of big ints, so we need to big set w0 to wins 0t. Because we're saying that the number of ways you can win after however many turns is equal to the number of ways of reaching the requisite score after that turns minus the number of ways the other player could already have won. So let's try that one then. Nope, I wrote set instead of sub. I actually think the multiplication might be slower than the duplicated work. So, yeah, I'm going to stop that. So we could do better if we did big add, big tump, but I can't actually remember if the big int library can safely add a number to itself. Like if you pass it two values that both point to the same big int, it's not immediately clear to me that trying to add them together will do the right thing. So to play it safe, we'll just do this. Yeah, that's better than it was before. It's about 10 seconds per turn. Don't think that's right, is it? 8601 and 2251. Yeah, that's nowhere near right. Let's go big int underscore prac. It occurred to me that we could initialize the big ints more easily by making this just go big int prac, and then we don't need this loop to initialize all the big ints, because all a big int is a bunch of, it's an allocation of however many words you need, and vzmalloc will set them all to 0 for us, so that will make the big int allocation take less time. So, why are we getting the wrong answer? Oh, I think we're subtracting off the wrong number. This wants to subtract off win of 1, t minus 1. And this wants to subtract off 0, 2. Because win for player of t counts the number of times we won the game at that turn. So we don't want to subtract off all the ways the other player has won on the previous turns. Oh, sorry. That's not the only problem. We also need to big add here, because win of player of t tells us how many times we won on that turn, not how many times we won on that turn or before. That's not right. No, this is right. I don't think it's possible for either of them to win after one turn, because the most you can gain in one turn is 10 points. So they'll be on at most 14 and 18 points. Therefore, we might be reading something out of the bounds of the table. Player position, turns, score. Well, there's no ways for you to get to anywhere on turn 0, apart from your starting position on 0 points, of which there is one way. So that looks fine. Oh. Yeah, okay. For a given player on a given position after a given number of turns, on a given roll, where do we end up? Well, the number of ways to reach the position we were already at on the previous turn is that. Multiplied by a number of ways to roll this roll. And we add it to the player for the new position, for the new number of turns, and the new score. Well, let's put some assertions on that then. Well, we know that S is less than 21. The new pos is less than or equal to 10, so this needs to be less than or equal to 30. Could we be reading from something out of range? Be 2-7 by Biggie and Crack. I don't think we need a global eye anywhere else. You're allowed to be on position player position. Yeah, you're allowed to be positions 1 to 10. Number of turns we're fast in, and score is less than 40. Ah, we changed the size of the array, didn't we? So it's no longer 40, it's now 32, so that will be the problem. Let's try that then. Turns minus 1 equals 0. That's actually fine. What a silly assertion to make. So one turn now takes about 15 seconds with all those assertions in there. So I'll definitely want to take those out. And hopefully there are 0 ways for either player to win after one turn. Great, yes! Ah, negative, no! How can he win a negative number of games? So the number we're subtracting off is too big. Because you've got the set of universes where player 0 wins after 3 turns, and you've got the set of universes where player 1 wins after 3 turns, and there's some the set of universes where they reach 21 points, let's say. And you can view them like this, and there's some overlap where they both reach 21 points on the same turn. Well, if they both reach 21 points on the same turn, then you do... Well, player 1 doesn't have minus 3,000 ways to win. If there's one way for player 1 to reach 21 points, and 2 ways for player 0 to reach 21 points, then player 0 wins both and player 1 wins 0. No, he doesn't. Player 1 wins on all of the games where player... Yeah, okay. So, this is wrong. What we want is... Player 1 wins. So we've basically got player 1 as one set of universes and player 2 as two sets of universes, and we want to multiply them together to get the answer. Player 1 wins in win 0t. That's the number of ways for player 1 to win in t turns, to reach 21 points in t turns, multiplied by number of universes where player 1 did not win in t-1 or less. Okay, I'm going to go and have a sit down and think about it, and I'll be back in a bit. Right, I'm back. I think this is correct. I think what I need to do to calculate this is have another one called lose. Maybe it's not lose, maybe it's just don't win. And then for scores greater than or equal to 21, we have to win. For other scores, we have to don't win. And that gives us a count of the number of universes in which a given player hasn't won after a given number of turns. So, we want to multiply win 0t by don't win 1 t-1. And then add it to that thing. Similarly, we need to multiply win 1t by don't win 0t, and then add it. And let's try that, that might be it. It would be really nice if the problem statement had a worked example for the sample case, showing you how many ways there were to win after each number of turns. Oh, I should have took the assertions out. However, if this gets the right answer, then I think it would be quicker to just run it on the real input and waste 30 seconds running the assertions than it would be to take the assertions out and waste 2 minutes recompiling the program. Okay, maybe this is looking more believable. I can't remember what it was supposed to be, but I don't actually recognise these numbers, so maybe that isn't correct. Also, why does player 0 win a smaller number of... because player 0 also wins... Must remember to take the assertions out. Yeah, so player wins in more universes. The game ends when either player's score reaches at least 21. I'm confused about why player wins in more universes. Because the number of turns player 1 has had when player 2 wins is equal to the number of turns player 2 has had. But the number of turns player 2 has had when player 1 wins is less than the number of turns player 1 has had. So surely there are more distinct universes in which player 2 wins than in which player 1 wins, because the universe stops splitting as soon as one of the players wins. Oh, hang on. Oh no. Well, we'll take the assertions out. I think my big problem is that it's not actually sound to treat the two universes separately. Ugh. We need to have a single table that has a column for player 1's score and that has a field for a dimension for player 1's score and a dimension for player 2's score, rather than having a table for player 1 and a table for player 2. Or do we? Why don't they just multiply together? If there are 10 ways for player 0 to have reached 21 points after so many turns, and there are 5 ways for player 1 to have done one fewer turn and not yet reached 21 points, every one of these possible universes can be combined with one of these possible universes, so why isn't the answer 50? So why don't you just multiply them together like this? So we definitely write into the table the only values greater than or equal to 21 in the table will be the ones where we've only just won the game, because we stop writing more after we've won the game, which we shouldn't do, because player 1, when player 0 wins the game, no, I think this might be correct. Once you've reached the point where you've won the game, there are no further universes past that point where the game takes place at all, either winning or losing. So what about this? So win P turns tells us if you were playing on your own, after how many as player P, and you've done turns, how many games do you win after exactly that many turns? So then if you're playing together, the number of games you win after that many turns is equal to the number of games you would win after that many turns multiplied by the number of games the other player hadn't already won. Why am I finding this so difficult? What? Do I need to assign to B? Did I just delete that when I deleted the assertions? I must have deleted that when I deleted the assertions, right? Turns -1. If we structured these functions the other way around, then we'd get to make use of the n ways multiplication more than once. So if we did the possible scores in the outer loop, so basically we've got calc going over 10 possible positions and then roll going over 21 possible scores. If they went the other way around, then we'd get to reuse n ways on all of the possible positions. But whatever. Oh no, we wouldn't. Or would we? I don't think so. Yeah, so I think that's the same answer we got before, which means I had accidentally deleted that assignment. And how big are these numbers? Are they too big or too small? I think they're likely to be too small. Too small. Am I not running enough turns? Let's run an extra turn and see if the score keeps going up. It shouldn't do, because we think you'll definitely reach 21 points after 6 turns, because the minimum you can score is 4. But if the score goes up even more, then I'll know I've got something wrong. Other than that, bit of silent contemplation, I think. The score will keep going up, otherwise there would have been no ways for the second player to win any at all on the 6th turn, because player 0 should have reached 21 points on the 6th turn. So you can roll a 3, and then if you're on position 1, that would be 3 mod 10, which is 3 plus 1, so new pos is 4. So S plus new pos, you should gain 4 points. That's annoying. Right. I really think 6 turns is enough, because the minimum you can score on each turn is 4 points. Because the minimum you can roll is 3. Your score is your roll plus your position, and the minimum position is 1. So you must, after 6 turns, you must have at least 24 points. So let's change all those 8s back to 7. And then see what the final output is. I'm surprised it doesn't have enough memory. Or am I? Not sure. That's correct. After 1 turn, player 0 can be at position 1. You score 1 in 6 ways. Well, how many points did he have to score to get to position 1 from position 4? 5, 6, 7, 8, 9, 10, 1. He needed to roll a 7. There are indeed 6 ways to roll a 7. To get to position 2, he needed to roll an 8. Yeah. To get to position 7, he needed to roll a 3. Yes, that all looks correct. So after 3 turns, how many ways can we... I'll have to write this down on paper. So player 0, after 3 turns, can have score greater than or equal to 21. In how many ways? Oh, there's more. So yeah, you can have, there's a lot of ways. So I'm not going to write these down. What we want to see though is that after 6 turns, or well, let's say after 3 turns, your score should be at least 12, right? Because you have to score 4 points every turn. So how can player 1 be on score 6 after 3 turns? Because you score what your new position is, which means the minimum score is 1, not 4. Darn. Which means we may have to do 22 turns. Which means it's not going to fit in memory. However, at every step, we only need to look at the previous. We only need to look at the numbers for the previous number of turns. So if we interspersed calc, add wins, then we'd only need to store 2. The turns column would only need to have 2 elements instead of all of the number of elements. That's what we'll do. But I'm pretty tired now, so I'm going to have another break. I'm going to have some lunch and I'll be back. Right, I'm back. I've got a filled belly and I'm ready to tackle this. So, rather than having 7 layers, we only want 2 layers. And instead of looking at turns minus 1, this just wants to toggle every time. So it's not turns and 1. So this is turns and 1. So where do we look at T? Yeah, okay, fine. Now, having calculated, we want to move these up here. And we'll just do this the way we did before. So add wins. This needs to move up as well. So we want calc 0t, add wins 0t, calc 1t, add wins 1t. Okay, so we don't need this anymore. And that's all fine. So we just need to move this loop below the add wins function. So what is it? Rt equals 1, Rt is less than 7. Something like that. And then where this looks at turns, I'd also want to be turns and 1. So we'll not print that. Before, when we were calling add wins, didn't we call it with t equals 0? Hang on, this doesn't want to be and. It only wants to be that when we're looking in table. So we just happen to know that I don't know if we'll actually need it. I don't think we'll need it, but that's correct, isn't it? There's exactly one way for either player not to win after 0 turns. And that's just their starting position. Okay, that's good, that's good. It looks at turns and 1. So is that right? Okay, I think that's right. And then instead of having the limit on turns be 7, the limit on the number of turns, you score at least 1 point per turn. So let's say after 21 turns, you'll definitely have got 21 points. But we need to let's try that then. Feel like I've forgotten something. be less than or equal to 21. Because we do want to check the 21st turn. So that's about 10 seconds per one, and we're doing 21 turns. 210 seconds is 3.5 minutes. Oh no, our 64-bit ints have overflowed. So I think we're definitely getting it wrong, because the number, it shouldn't be anywhere near that big. So there's one way to roll a 3, there's 3 ways to roll a 4, so we definitely want, when we add on a roll of 4, we definitely want to gain 4 times as many universes as there were before. Well, I thought this wasn't needed, so it might not make any difference, but it should be that. Yeah, I don't think that makes any difference because it's always multiplied by 0 anyway. Why is it 28 after one turn? Should be 27 possible universes. They're all one more than they should be. So after... I think don't win 0 1 should be 27, not 28. 1 plus 3 plus 6 plus 8 plus 6 plus 3 plus 1 is indeed 28. So what's the error here? I think I've got the number of possible rolls for the dice wrong. Since the 3 and the 6 are obviously symmetrical, it must be one of the 1s or one of the 8s that's wrong. Well, let's brute force that then. There are only 7 ways to make 6, not 8. Good. 27 universes after your first turn. 730. Well, 27 squared is 729. So how are we getting to 730? So 730 times 27 is 19,710. What do these numbers add up to? 19,737. So we're adding on, don't win 0 3 includes all the number of ways not to have won at turn numbers smaller than 3. Because, no it's not, it's just got 27 extra. Oh, I know why. When we reuse a row from the table, we need to zero it out again. Where was that? Yeah, so at the start of a turn, we need to zero out a row of the table. Ugh. Player position, turns 1 2, score. Turns less than or equal to 10, score less than 32. Table, player, position, turn more 2, score. And the same for the other player. Right there. 4608 plus 15075 is 19,683. 27 times 729 is 19,683. Good. That looks like we're on the right track. We now have the correct number of universes at every level. Or at least for the first 3 levels. Well, let's check them as we go. Oh no. Yeah, because we only get 27 more universes for the universes we didn't win. Okay, good. Go on. And don't win is now going down again, which is good. Great. Yeah, this is behaving much more sensibly. Because now we're getting to the point where the majority of universes have already won. And are these numbers about... Well, we're going to multiply it by number from the other one, so it should be about... Oh, we only need to do 10 turns. Can we prove that we only need to do 10 turns? Not obvious. So I don't think I'll change it yet, because although we can break once both the don't win values are 0. That's what we'll do. Because if don't win is 0, then there cannot be any more, then there are no more universes. I don't think those numbers are actually correct. Although we're obviously getting closer. It's the right magnitude. Find the player that wins in more universes. In how many universes do they win? So we actually don't need to print the difference out at the end. Oh, it is the correct answer. Great. We don't want the difference. And we don't need to print these out. And what I'll do is don't win 0 T is 0. Well, as soon as either one of them becomes 0, I think it's the end. Someone at the door. Yeah, so we'll stop as soon as both of them are 0. Probably don't need to format them either. But I think we're pretty much there. Great, that all looks correct. I checked it with a calculator. I don't actually think we need to carry on though. Why are we carrying on? Is the other player not finished yet? Ugh. If we were going to do all these turns anyway, I'd be better off just running it and not recompiling it. What did I get wrong there then? Oh, I wrote big cump instead of big cump W. So it's comparing it to the first 4 words of the bootloader wrong. Darn. What a waste of time. I should have just run it without recompiling it. And you might be thinking, well, I would have just run it without recompiling it. But remember, that's easy for you to say because I edit out all the long, boring parts in the video. Meanwhile, I'm sitting here in real time watching it print out zeros for 3 minutes. So we just submit whichever one of these is larger, presumably player 0. Day 21, yes. 499821. Oh, I did type me. 499821 658 61983. 658 61983. Now that better be right. Otherwise, I do not know what to do. Yes! That was a good puzzle. I enjoyed that one. Well, I enjoyed it for a while. It eventually the slowness of my computer began to wear on me. Yeah, great stuff. Thanks for watching. Goodbye.